Hey guys, welcome back to AP Physics C Mechanics. Today we're going to be talking about the dynamics of particles, which involves Newton's second law, and we're going to be doing that in chapter 5 of our textbook. This is section 2. We're just going to talk through a couple of things and do several examples. Should be conceptually stuff that you know, but just in case you need a refresher, here it is. So last class we talked about particles in equilibrium, which is where the sum of forces equals 0. Today, instead of the sum of forces being equal to 0 and being in equilibrium, we are instead going to be specifically not in equilibrium. Sum of forces is not going to equal 0. Instead, the sum of forces is going to equal mass times acceleration. Now, this is a more general case, meaning it applies to every question, really. In equilibrium, that's a special case because it only applies to balanced forces. But if you do equilibrium here with Newton's second law, the general case, that would be equilibrium is with constant velocity, so acceleration is 0, so mass times 0 ends up just being the equilibrium condition from yesterday. So you can use Newton's second law at any time, even if the particle is in equilibrium. That would just simplify down to the special case that we discussed last time. And here it's easy to see force is a vector and acceleration is a vector. So we are of the same type on each side, but here we're multiplied by mass, which is a scalar, okay? Now when you multiply a scalar times a vector, so this would be mass times acceleration. If your acceleration vector was, we'll just do one in each direction, I plus j plus k. That scalar distributes to each term of the vector, just like in normal mathematical distribution. Multiplying scalar by vector is just distribution, nothing crazy, nothing wonky. That would just be mi plus mj plus mk. We're just distributing. Multiplying by a scalar by a vector, simple distribution. When you multiply a vector by a vector, you got several different options and it gets a little bit crazy. We're going to see that later on in the course. So here, all that Newton's law really says is that your sum of forces has to be equal to the mass of the object times its acceleration. And it says acceleration is going to be the same direction as the force. Acceleration is the same direction as force. And then also it's going to be proportional to the mass. So if the mass goes up, the acceleration goes down. If the mass goes down, the acceleration goes up. Okay, it is a lot easier to accelerate. It takes a lot less force to accelerate small objects than it does to accelerate large objects, so on and so forth. You guys know those relationships. I'm not going to go super far into them. Instead, we're going to hit some examples. So here in example 5.6, we've got an ice boat at rest on a frictionless horizontal surface. Okay, and we got a picture that I'm going to go find. All right, there is our lovely little boat, ice boat. I've never heard of an ice boat before. New concept, cool concept, I guess. Is it really a boat if it's on ice? Great questions. Anyway, the real question says, due to the blowing wind, 4 seconds after the ice boat is released, it is moving to the right at 6 meters per second, 22 kilometers per hour, 13 miles per hour, but 6 meters per second is what we care about. Ask what is the constant horizontal force, Fw, that the wind exerts on the ice boat. Okay, and then it gives you the combined mass is 200 kilograms. So first things first, we need to draw a free body diagram. That's the big deal. Okay, now I'm going to get rid of this picture here, and I'm going to draw my own free body diagram. Picture's there in the book if you still need it. Okay, for your free body diagram, you're going to want a nice coordinate system, preferably with straighter lines than that. Okay, and you got to decide your positive and negative. I'm going to choose conventional here with the x's, y's, positives, and negatives. So you set up your coordinates, you put your object there in the middle, and now we've got to figure out some of the forces here. So it says we're on a frictionless surface, so there's going to be no friction, but we are probably on Earth, so we're going to have some gravity pulling us down, force of gravity, and that's always equal to m times g. We happen to know the m, is 200. You don't have to put this on your free body diagram if you don't want to, but I like to sometimes. Times 9.8 is what we'll be using for G. Okay, so we got force of gravity. We know the mass, so we can calculate that there if we want to. Actually, let's go ahead and do that. That's like 1,960. Yeah, something like that. Now we're also going to have the normal force. Okay, and the boat's not flying, the boat's not falling. So normal force is going to be equal to the gravitational force, but we'll see that in a minute through other methods. And there's no friction, but it is blowing to the right from the wind. So we're going to do that force W, force of wind. Perfect. That's all the forces. Now we got to do sum of forces. The sum of forces is going to be everything in the x direction. So that's a positive FW times I hat plus everything in the j direction. That's FN, FN, and then minus FG. You can write FG if you want here, or you can write MG, or you can go ahead and write the number. I'm writing 1960 because I already know what it is. And that's in the j hat direction. Perfect. Now we know, due to Newton's second law, that this has to also be equal to m times the acceleration vector. Now, for the acceleration vector, we've got some givens in the question. It doesn't tell us straight up what the acceleration is, but it says due to the blowing wind, 4 seconds after the ice boat is released, it is moving to the right at 6 meters per second. Okay, now we are going to have to assume, I hate assumptions, but we're going to have to assume that this is a constant wind, constant force. Okay, so we know acceleration is dv dt. Okay, so to get the velocity function, you just integrate with respect to t. So you'll have at plus initial velocity equals your velocity, and that's as a function. So we're going to assume the a is constant, and it says it's released from rest, or it's at rest when it's released. So the v naught initial is 0. So the acceleration times time equals the velocity at any point. Now we know that 4 seconds after it's released, it's moving at 6 meters per second. So that's acceleration times 4 equals 6 meters per second. That's to the right, so those are both in the, or so that has to be in the I hat direction. Yep. So then we divide by 4 on each side, and you get acceleration has to be equal to 3/2 I hat. Now you probably, being the smart person you are, could have done that in like half a second just looking at the givens. And you're welcome to do that, but this is the technically correct method. You get acceleration is 3/2 I hat. Now I'm going to erase that and plug that acceleration into my equation. So I've got force of wind I hat plus force normal minus 1960. Oh, that should be a j hat. I don't know why I didn't I hat there. That should be j. Somebody correct me when I do dumb things, except you can't because this is a video. And that equals mass times your acceleration, which I said was 3/2 I hat. And if you want to, you include a plus 0 j hat if you like. One other thing you can do here is substitute 200 in there for the mass, since we happen to know that already. Equals 200 right there. Now we just got to set these things equal to each other. The force of the wind I hat has to be 200 times 3/2 over, or 3/2 I hat, so that's 300 I hat. And then force normal minus 1960 has to equal 0. So you get, and that's all in the j hat direction, force normal equals 1960 j hat. So there's your force of wind. You've also got the normal force, which you didn't really need, but you could solve for anyways. The next example that we're going to do is example 5.9. We're going to actually skip 5.8. But 5.9 is about apparent weight in an accelerating elevator, which is a little bit different of a concept. So we're going to talk through it. The question says, a 50-kilogram woman stands on a bathroom scale while riding in the elevator in example 5.8. Oh, and there is, you can go look at 5.8 for the information about that. I'll pull it in as we go. While the elevator is moving downward with decreasing speed, what is the reading on the scale? So some things we know from the other question is the elevator and its load have a combined mass of 800 kilograms. And we know it's initially moving downward at 10 meters per second. So we should go ahead and set up a coordinate system somewhere so we can draw that. Really, we're not doing any left and right motion, only up and down, one dimension. So I'm just going to draw this axis. We're going to make up positive and down negative, as is tradition. You don't have to do that if you don't want to. But you've got your velocity initial is negative 10 j hat, vertical. And it slows to a stop with a constant acceleration in a distance of 25 meters. Okay, so this means that over some amount of time, it's slowing down. We've got an acceleration is some constant a, and that's in the j hat direction. And from there, we can figure out a velocity function and a position function to incorporate the fact that we know it goes down 25 meters. So to get the velocity function, we'll integrate the acceleration function. Velocity equals at plus v naught in the j hat direction. And we know that the v naught is negative 10. So we can go ahead and replace that there. And then define the position function. Integrate again. So you got 1/2 a t squared minus 10t. And then you would do the initial position. We're going to call the initial position 0, so we can eliminate that term. That's j hat. And one other piece of information from the example 5.8 is we know that at some time t, we'll call it t prime, that it slows to a stop with a constant acceleration in a distance of 25. So at some time t, whenever it stops, we know that the distance is 25. And then also, you'll know that the velocity at that point in time is 0. So velocity at t prime equals 0. Those are both j hat. And actually the 25 is negative 25 because it's going to be moving downward. And that was all from example 5.8. So what you're going to need to do from there is find your acceleration. And that's going to be a little bit gnarly. I'm going to erase my coordinate system so that I can deal with that. Okay. So what we're going to do here is use our conditions that we know. We know r of t prime is negative 25. So we can plug in t prime to our lovely position function. Ra t prime squared minus 10 t prime equals negative 25. And then we also know that a t prime minus 10 has to equal 0. And that's from our velocity function. So we can solve this for t prime pretty easily. Once we have the t prime, we can plug it into the other function. So if we solve that for t prime, we get it is 10 over a. Now we're going to plug that into this equation. 1/2 10 over a, or sorry, a first. A times 10 over a squared, so that's 100 over a squared, minus 10 times 10 over a, minus 100 over a is what we get there. And that equals negative 25. Now I got to do some algebraic wizardry. You get 50 over a minus 100 over a equals negative 25. If you simplify this down, you get negative 50 over a equals negative 25. Rearrange that and you get a is 2. And that may give you a little bit of pause for a second, okay? So the elevator is going down, but its acceleration is positive, and we define down as negative. Well, the reason is because we're slowing down, the acceleration is actually in the positive direction. So from there, you got to do a little bit of kinematics work to get A is 2. There is a kinematics equation that takes care of that real quick if you'd prefer to do that. Okay, but we're doing the technically correct calculus notation. That way, whenever you have more complex functions, you can do it this way when it doesn't work out with kinematics. This way you could do your regular kinematics equations because your acceleration is just a constant. But if it was something weird where acceleration wasn't, you'd have to use this method. All right, so I took all that information away so we could have some more blank space, but we got the acceleration is 2 j hat when our coordinate system is like so, positive, negative. And we know the mass of the whole thing is 800. Now we need to do a free body diagram here for the woman because that's what we care about. Or more specifically, with apparent weight, what we care about is how much force she is exerting on the scale. But in order to do that, we need to do a free body diagram for the woman. So here is my dot, that's a woman. And on the woman, there are some forces, okay? One of them is gravity, force of gravity, which is equal to her mass times the acceleration due to gravity. We're on Earth, so that's 9.8 meters per second squared. Now you also have a normal force from the scale. And that's what we're going to be looking for. Whenever you're doing an apparent weight on a scale, you're looking for the normal force that that scale is having to provide on your person, okay, or on your object that's on the scale. So we're going to be looking for that normal force. Now there's nothing pushing side to side, and there's nothing else pushing her up and down. She's literally just standing on the scale. That's the only contact, so that's the only force besides field forces, gravity, electricity, magnetism. She's not an electric charge, she's not a magnet, so only gravity do we have here. All right, so one thing we do know is that when you're riding in an elevator, you go at the same rate as the elevator does. If the elevator is accelerating at 2 j hat meters per second squared, then you're accelerating at 2 j hat meters per second squared. Okay, you're constrained to be still on the elevator. Okay, no, her acceleration 2 j hat, her acceleration is the same as the elevator's, which is 2 j hat, and then the mass that we have here, the 800, is actually for the elevator. Okay, we don't care about the elevator right now. We care about the lady, and the lady is 50 kilograms. So what Newton's second law says is we can sum these forces. We've got sum of forces equals normal force, which is positive, minus 9.8 times the mass, and that is in the j hat direction. We can go ahead and do the 9.8 times the mass. That's like 490. Yep. Sum of forces equals normal force minus 490 j hat. And Newton's second law says since we are accelerating, this equals mass times acceleration. So we can plug in our acceleration function there. You get Fn, normal force, minus 490. I'm going to drop the j hat because everything's in j hat, equals mass, which is 50, times acceleration, which is 2. So that has to equal 100 newtons. And you add it on both sides, you get normal force is equal to 590. So her weight there is 590. And what that does is it makes her feel heavier. So when the elevator is slowing down, she's going to feel heavier, have more apparent weight. Now, it's not going to change her mass, okay? We don't do an apparent mass because mass is literally the amount of matter in an object, okay? We're caring about apparent weight. That's the apparent force that is on her. So that's going to be 590 newtons. And if the elevator were accelerating downward instead, say, or speeding up going down, and you had a negative acceleration, that would be negative 100, and you would actually get 390 instead of 590. So if it's accelerating downward, your apparent weight is going to be less, which is why sometimes on elevators, when they drop, you get that little lurch in your stomach, okay? You feel slightly weightless there for a second just because your apparent weight drops so much in that one instant where you're accelerating super fast. All right, so I just looked at the rest of the examples in the book, and they are very similar to ones that we did in the previous lesson, just where instead of saying the sum of forces is equal to 0 because we're at equilibrium. You just say the sum of forces equals mass times acceleration and solve for there, or from there. So try to solve these problems on your own. I'm not going to go through those examples because they're very similar to things that we've already done. The only potentially tricky thing is that you will sometimes have constraints on that acceleration, where if two objects are attached, two objects are attached, they have the same acceleration. So if a weight is going over a pulley and pulling a box, okay, those two have the same acceleration, so you have to constrain it to that. That's really the only thing that is new. The acceleration of two connected objects is going to be the same. It's constrained in that way. All right, guys, let me know if you need anything, if you want the rest of the examples from this section. Next time, we're going to be talking about frictional forces, which includes air resistance and rolling friction and terminal speed. Okay, so that's going to get a little bit into the calculus there, and maybe a tiny baby smidgen of differential equations. Okay, so it is going to start incorporating the calculus there, but I'll see you next time for that. Today, just make sure you got down regular Newton's second law, F equals ma.